much. It's a fantastic pleasure to be in India for the first time and to be giving you many talks, which I've learned from the talks I've already seen that I don't need to encourage you to ask questions. Feel encouraged anyway. But no, I mean, please do. So the talk now and then the next 2 days are kind of connected. The colloquium will have a lot of redundancy with this and later talks, and it will be a little bit simpler. But the main theme of the 3 talks is trying to understand black hole thermodynamics and the black hole information paradox, and relatedly, as we'll see, bulk locality by studying ADS3 CFT2. The kind of key idea is that a huge amount of information about black hole thermodynamics in ADS3 is encoded in the symmetry of the conformal symmetry of the Virasoro algebra. And so that makes it possible to do a lot of things that you might have thought would be forbiddingly difficult. Now, the first lecture will not be doing anything particularly surprising or difficult. The first lecture will be all about kind of connecting nicely with the talk we just saw and the very nice talk yesterday. Today I'll mostly be talking about how we derive black hole thermodynamics just in the limit of classical gravity from conformal field theory. And so it'll sort of make clear why the Virasoro algebra really sort of knows about things like BTZ black holes. The talk tomorrow, I'll be studying exponentially small corrections to black hole thermodynamics, the sort of non-perturbative effects in G Newton that I believe are associated with solving the information paradox. And then in the third talk, we'll sort of go into the bulk and talk about local bulk correlation functions, again, using this power of Virasoro symmetry to say something not just about perturbative gravity, but about non-perturbative gravity. So that's sort of where we're headed. Virasoro algebra is kind of the key theme. It means that instead of having to solve a full conformal field theory exactly, which seems kind of close to impossible if it's a chaotic CFT that's dual to holographic gravity, we can look at this subsector of stuff that's fixed by symmetry, by Virasoro symmetry, and make a lot of progress that way. So that's sort of globally where we're headed. The motivation for the lecture we'll see today is just understanding universal features of ADS quantum gravity directly from conformal field theory. And so the first part will make contact with the talk from yesterday. I'll talk about ADS locality, why in a certain sense all conformal field theories can be thought of as objects moving around an anti-de Sitter space where the interactions are local, at least at long distances. And furthermore, why things like the long-distance gravitational force is actually completely universal. And then the second part of the talk, I'll address how we can derive the full nonlinear gravitational field, not just the long-distance force, in ADS3 using Virasoro. And then I'll, if I have time, there'll be some speculations that connect nicely with Raghu's talk about what kind of CFT data actually governs thermodynamics, and maybe some other random speculations as well. So I think something that I've spent a lot of time doing is trying to generalize some of these ideas in ADS3 to higher dimensions, and I've mostly failed, but there's a lot of open questions remaining that I can tell you about. So the outline is we'll talk about long-range locality. I'll give you sort of an interlude about ensemble thermodynamics versus microstate thermodynamics. How do we associate a temperature with a pure state, as in the title? And then we'll use Virasoro symmetry to actually derive results. So this is really a recap, so you can either delay me by asking questions or you can encourage me to go faster. But just so we're all on the same page, I'll basically, throughout all of these lectures, be thinking about ADS CFT in global coordinates. That means that ADS looks like this, the inside of this cylinder. The time evolution operator in ADS, the Hamiltonian in global coordinates, is the dilatation operator of the CFT. It's stretching out concentric circles if we think of the CFT as living in the plane. That means that energies in ADS, which are quantities that physically we'll often care a lot about, like what is the Planck scale, what is the mass of some particle, et cetera, correspond to dimensions of operators in the CFT. And you convert between them just by multiplying by the ADS length scale, which I'll basically always fix to 1, but you should always keep in mind. So that's how a dimensionless quantity like a scaling dimension turns into an energy in ADS. Another basic point that I'll sort of have in mind, especially with respect to understanding locality, is that irreducible representations of the conformal group correspond to basically the center of mass motion of some object in ADS. So we often talk about a primary operator and its dual primary state in a CFT. That corresponds to some, if we think about it in terms of ADS, that corresponds to some object whose wave function is localized in the center of ADS and it's just sort of sitting there. Descendants of a primary state, the other non-trivial states in your rep of the conformal group, correspond to sort of motions of the center of mass. So the center of mass of our object can sort of slosh back and forth in ADS, or alternatively, it can orbit around the center of ADS because intuitively you can think of ADS as having some sort of central force that gets stronger and stronger as you move away from the center. And so objects with angular momentum quantum numbers are just on orbits around the center of ADS that circle around. As was anticipated by all of our discussion yesterday, a basic question you can ask about any quantum mechanical theory is, the coarsest, most basic notion of locality is, does the theory have a Fock space of states at large separations? So here we have dogs and cats scattered through the universe, and the point here is that once we know that it's possible to have a dog, we can create quantum states where we have a dog here and a dog in the Andromeda galaxy. They don't talk to each other much, and for example, both dogs like to play fetch equally well, but they don't know about each other when they're playing fetch. So in other words, so this is sort of the question of the most coarse version of locality that we can ask about. Now, it turns out in ADS, we can ask this question in a very nice controlled way, which isn't necessarily available in flat space at the level of the Hilbert space. So given a state involving, say, a dog and a cat, we know that there exists a state for a dog and a state for a cat. We can ask, do there exist states where a dog and a cat are very, very well separated from each other, where we separate them by giving them large relative angular momentum? Because the basic states in ADS can orbit around the center just kinematically, not because there's an externally imposed force, but just due to the kinematics of ADS CFT, we can ask whether or not there are these sort of states involving a cat and a dog orbiting each other at large spin. And we know that just, again, kinematically, that the geodesic separation between a cat and a dog grows as the logarithm of this angular momentum. So we can ask a very sharp question, which was discussed and answered yesterday, which is, are there multi-object states at large angular momentum? And more precisely, since the energy in ADS, or the Hamiltonian in ADS, corresponds to dimensions in the CFT, we can ask, do there exist, given a cat and a dog, does there exist a state with energy equal to the energy of the cat plus the energy of the dog, plus some kinetic energy, plus some term that goes to 0 at large separation or large spin. So this is this thing that we call the anomalous dimension in conformal field theory, but in ADS you just call it the binding energy between these two objects. It's the energy corresponding to the force between them. So if these states exist, and gamma goes to 0 at large spin, then we have a form of coarse ADS locality, and it turns out that that's just a CFT theorem. Given any operator O1 and an operator O2 in any CFT in 3 or more dimensions, there always exist states in their OPE that are these large spin states with this dimension, and the anomalous dimension goes to 0 at large spin at some power law rate that's fixed by the smallest twist operators that can be exchanged between O1 and O2. And the most generic thing that you can always exchange is conserved currents, and specifically the stress energy tensor.
Yeah, I'm sorry. If you notice that 2n is coming from...
So these are both kinematic numbers. The L, of course, is the rotation. The 2n is the sort of breathing mode where they can kind of slosh back and forth towards each other. If n and L are both large with some fixed ratio, then basically, semi-classically, you'd think of this as some sort of eccentric orbit where they're not on a circular orbit around each other, but they're sort of doing something sort of like this. So, I mean, formally, this theorem says that for each fixed n, there exists this tower of operators as L goes to infinity. And that's because, I mean, if you take n to infinity with L fixed, then you're studying some sort of scattering process where they basically come slamming into each other. And that's not local. I mean, you're not keeping them separated in that case.
The geodesic distance being a log is translated into this power because there's an exponential.
Precisely. So in ADS, of course, there's this fact that the surface area of a sphere of radius r grows exponentially with r. And that means that all forces, even those mediated by massless particles, fall up exponentially with distance. And that's why this power law translates into an exponential. Oh yeah. So this is in angular momentum, and then this is supposed to be an exponential, and kappa is supposed to be a geodesic separation. And the idea of the proof of this statement, if you didn't already glean it from earlier today and yesterday, is that there's some singularity in one channel, which in the context of scattering amplitudes you might think of as some t-channel singularity associated with, say, some exchange. And this singularity occurs as in the forward limit when cos theta goes to 1. In the other channel, you just have a sum of Gegenbauer polynomials in cos theta. You can never get a singularity from any finite number of spins. You have to have an accumulation of infinitely many spins in order to reproduce this behavior. And translating this from scattering to the bootstrap is how you prove that these large spin operators exist. Okay, so just to emphasize the connection here with gravity, universally there's this contribution from the stress energy tensor, because any operator O with itself and the stress energy, any operator O in its OPE with itself has the stress energy tensor appearing. Now in ADS CFT, we like to say that the stress energy tensor is dual to the gravitational field. And very specifically, what that means is that the stress energy tensor, when it acts on the vacuum, creates a state that corresponds to a graviton sitting in the middle of ADS. Because of CFT ward identities, the OPE coefficient of any operator with itself and the stress energy tensor gets a contribution which is proportional to its dimension. And we normalize here by the square root of the central charge. This vertex is exactly what gives us Newton's law in ADS. The fact that this exchange of the stress energy tensor is proportional to delta 1, delta 2, or delta heavy, delta light over the central charge is what gives us the force law G Newton times M1, M2. And so by using the bootstrap, we can learn that gravitational forces at long distances are completely universal. And this is, in a certain sense, kind of like an ADS-CFT analog of Weinberg-Soft theorems. We're using symmetries and ward identities to tell us that long-range forces are very universal.
I'm very sorry, I should know this, but how is the Newton law supposed to go in ADS-3?
Well, this is just the overall coefficient. Oh, good. So this is a good question. So in higher dimensions, the force falls off with distance. In ADS-3, if we have two, I mean, I haven't talked about ADS-3, but in ADS-3, if we have a sort of heavy but not heavy particle that isn't a black hole, then it gives rise to a deficit angle. What that means is that the potential at long distances is actually finite. So at very, very, very large separations, there still is a shift in the energy of this two-particle state due to their interaction because of this deficit angle. And that also can be obtained in this way.
Distance independent.
It's distance independent. Yeah.
So that says something about anomalous dimension.
Indeed. So you can ask what is the spectrum of these two particle states in ADS3. So I briefly said under my breath when I was mentioning this theorem that this theorem is true in for CFTs in 3 or more dimensions. For 2D CFTs, the story is a lot richer because of these effective long-range forces. And so you can ask what is the anomalous dimension, but the anomalous dimension, instead of being something that vanishes as at large spin, it's just some finite correction.
Sorry for trolling, but
Yeah.
what about ADS2? Like how like everything changes obviously, but there's still stuff here.
In ADS2, there's no angular momentum, so we can't. There's no L quantum number, so there's just sort of nothing. None of the sort of this theorem survives. I mean,
I don't even think you can have excitations. Okay.
yeah. Good. So all of that was really to motivate the question, well, okay, so we learned about long-distance gravity in this very universal way from the bootstrap. So the question is, what about the full nonlinear gravitational field? Can we get that from the conformal field theory as well? Can we think about it as a sum over some exchange of states and learn about things like black hole thermodynamics, which depend on much more than just the long distance behavior of the field, but also know about, in terms of Feynman diagrams, every possible diagram you could tell.
So when you're going to become more precise, you want a gap in the spectrum or not?
Well, I'll be more precise about that in many slides when we do it in ADS3 CFT2.
I mean, you're talking about the long distance force due to gravity, but there's a dimension 6 operator that also gives you a long distance force.
Good. So when I talk about the long distance force in the last few slides, I'm talking about the leading thing at long distances. I mean, all of the low twist operators can contribute. So if there are other conserved currents, those also give you equally long distance forces. And then other things are all, there'll be some gap to everything else, unless there's some accumulation where you're arbitrarily close to having an infinite tower of higher spin currents.
So do they need to be affecting currents or they could just be
They have to be conserved currents to compete with gravity at very large distances. The only things that have so there's a unitarity bound on the twist. So for I can say that for L bigger than or equal to 1, the twist has to be bigger than or equal to d minus 2. And if it saturates, then we have a conserved current. There's also a statement that I think helps with there being a gap, which is that there's this Nachman theorem that says what the shape of the twist has to be as a function of spin for the lowest twist state at each spin. And that's what we're interested in here. And that says that has to be growing, but it's concave down. So as you go to larger and larger spin, you don't approach this bound once you've sort of exceeded it. Okay.
Just to understand, so suppose you have this large angular momentum operator, you
Yeah.
get almost a sum of two things plus some small power law operation in L.
Yes.
And then there would be other power law operations.
Exactly. Yeah. So there will definitely be many subleading power laws. This is only about the leading one. Okay. So before trying to address this question of getting the full nonlinear gravitational field, I'm going to briefly talk about how to think about thermodynamics.
I suppose, I'm sorry.
Yeah, go ahead.
Suppose the operator, is it impossible for the, it's possible, right, for the theory to have a lower twist operator than the stress tensor?
It has to be a scalar. So you can have scalars with twist less than d minus 2, but anything with spin 1 or higher has to have twist equal to d minus 2 or bigger.
So suppose I have a scalar between dimension half and dimension 1 and 3 dimensions, then that dominates the problem.
That dominates over gravity at long distances, absolutely.
So I wanted to ask exactly that. So let's say we take that scalar example.
Yeah.
How does the force law go with distance there? Do you know? I mean, what?
Well, in physical distance, it's still exponentially falling. In spin, it's still a power law. It's just that the power law is a sort of less quickly falling power law than the stress tensor. So at very, very large distances or equivalently very large spins, it's the biggest effect.
It's still falling exponentially with distance. Just
Yes.
Because, volume goes so fast in ADS.
Yeah.
But the power of that is small.
This is smaller, yeah, exactly. So the power is always just given by, I wrote it down somewhere. The power in terms of physical, this is geodesic separation. The power is always just the twist. It just, and the twist is always positive if you satisfy the unitarity bound. So,
Thank you.
sure. Okay, so let's talk briefly about thermodynamics. So most often when we think about thermodynamics, we think about it as some statement about an ensemble. So for example, we talk about the canonical ensemble and we study the partition function where we sum over all states, we count the number of states with some e to the s, and we have the suppression by a Boltzmann factor. And in the thermodynamic limit, we can relate the entropy and the temperature in a simple way by just ds dE is 1 over T. But of course, here the temperature is really just a part of the definition. I mean, we define the partition function observable at finite temperature. And we're interested in computing the entropy from this point of view, i.e. the number of states as a function of the energy. And the kind of thing that we do is we say, we study things at finite temperature, and then we derive the Carty formula for the number of states as a function of energy. But there's another perspective we can take, which is that of eigenstate thermalization and microstates. So of course, when thermodynamics makes sense at all, we expect that almost all physical observables are the same in, say, the canonical ensemble at some fixed temperature, or in the background of some specific microstate with an energy that means that it's generic for that temperature. So in other words, we can study correlation functions in just some heavy microstate background, and then we can ask whether or not this correlation function looks like a correlation function at some finite temperature, which presumably will depend on the energy of this microstate. So instead of talking about fixing the temperature and then, for example, studying the entropy as a function of energy, we can study a state with some fixed very large energy, and we talk about whether or not this looks like a correlation function at some temperature that will depend on the energy. And of course, this kind of idea is related to the eigenstate thermalization hypothesis, the idea that the eigenstate thermalization hypothesis is some very specific proposal for what correlation functions look like in a microstate background such that their matrix elements imitate this. So in, of course, this talk, our notion of the thermodynamic limit will be not necessarily the usual notion of thermodynamic limit of an infinite size or an infinite volume, but it'll be the thermodynamic limit of large central charge, sort of intuitively large number of intrinsic degrees of freedom, and energy of order the central charge. Okay, so to make this precise in the context of ADS CFT, we'll be studying this very specific observable, which is a conformal field theory 4-point function of 2 heavy operators and 2 light operators, where we think of this as a heavy operator acting at the beginning of time and creating some very, very heavy state. Then we conduct some experiment with light operators that probe that state, and then we destroy the heavy state at the end of time. And this looks like having some either heavy particle or maybe a black hole sitting in the middle of ADS space probed by some light operator. So you can do a bunch of things with, if you know this 4-point function, you can learn a bunch of facts from it. One is you can, you expect that if there is a good holographic description of your conformal field theory, then this should be a probe of the geodesic length in the background of this heavy operator, at least in the limit where this light operator isn't so light, it's sort of some heavy semi-classical particle. And so if you know this 4-point function, you can learn something directly about the geometry by measuring the lengths of geodesics. Yeah?
Is this separated in real time in the point, or are we?
In order for these to actually touch the, reach the boundary, they're separated in Euclidean time.
Okay.
But yeah.
Yeah, because if they're purely time-like,
Then the geodesics never reach the boundary. Absolutely,
you
yeah.
have to get the real-time correlator somehow by analytically continuing the geodesic length.
Indeed, yeah.
So
Yeah.
the heavy state is something which is homogeneous in the field theory,
Mm-hmm.
but in the EDS you are sort of depicting the straight geodesy.
Yeah. Why is that? So I'm viewing this as this is just some primary state in the CFT. And in terms of their center of mass, primary states in ADS have wave functions that localize them near the center of ADS. Now, this heavy operator is creating a completely general heavy state. We don't know anything about it so far. So it could be some extended object. It could be like a galaxy that's sort of moving around. And so this line really is only telling me about where its center of mass is. It might have all sorts of effects at long distances. And I mean, that's something that hopefully that we can detect from studying this correlator. But
But if it's in the center of ADS, then its shadow on the boundary is probably.
yeah.
So it's
Yeah.
whether there is slightly off center, then it would be localized.
Yeah. Then it would move back and forth. Yeah, so I mean, this is acting at the origin in the plane, which is sort of uniform on the circles. Okay, and then of course the other thing that we can try to do if we have this 4-point function is we can probe whether or not it looks like a thermal correlator. So what do we mean by it looks like a thermal correlator? Well, as we just discussed, thermal 2-point functions should be periodic in Euclidean time. They satisfy the KMS condition that was just reviewed for us. And so we can observe whether or not this correlation function looks like it's thermal and read off what temperature it has simply by looking at its periodicity properties in Euclidean time. So that's a very simple thing that we can study. And if we know this 4-point function, we can therefore read off the temperature just by doing this very simple thought experiment. Good. And yeah.
So just to understand, you're saying, so you take one very heavy state and another moderately heavy, which you were calling light, so you can use the geodesic approximation, and you can still see this thermalization.
Good. So here it actually doesn't even matter whether this is very light or just kind of light. A question that I can ask is, does this 4-point function have an interpretation as a 2-point function at some temperature? And the only thing I have to do to check is ask whether or not it's periodic in Euclidean time. And then the periodicity will tell me what the temperature is. So this is a way of taking some heavy state with some energy that I know and reading off a temperature. So it gives me temperature as a function of energy. If I know temperature as a function of energy, then I also can, assuming thermodynamics holds, I learn the Carty formula as well, because I can convert from temperature as a function of energy to entropy as a function of energy, assuming the canonical and the microcanonical ensemble are the same. So that's how, by studying this pure state background or this heavy light 4-point function, I can sort of deduce thermodynamic properties. Just as an indication of sort of what we'll talk about much more in the next lecture, there's also some sort of mini black hole information paradox hidden in this, or at least there's some set of questions we can ask, because if we study the background of some specific pure state in the theory, it can't look, the correlation functions can't look exactly thermal. There should be some deviation from the thermodynamic limit. And those deviations from the thermodynamic limit are encoding details about the difference between one pure state and another pure state. In other words, they're encoding the information that's stored in black holes. And so figuring out the exponentially small deviations from what in this case is the thermodynamic limit is really telling us something about black hole information. Yeah.
Can I think of this periodicity as, this may be wrong geometrically, but can I think of it as moving the other particle up along the cylinder? And then and then it's periodic because if you move it some length, then particles have time to go inside, bounce back, and come back.
So there's a Lorentzian periodicity in empty ADS. That's not the thermal periodicity.
That would be much longer.
Yeah, that's a sort of ADS time scale thing. This is a Euclidean time periodicity.
That can all be visualized like that, right?
Yeah, I mean, if the correlator looks thermal, then it looks like it's a correlator on S1 cross something, and then I can sort of think of it as. But I mean, this is something you observe purely in Euclidean space.
So the correction, the finite central charge correction, what type are they?
Well,
1 over 3 type of.
So, I mean, there are things that are 1 over C correction. I mean, there are 1 over C corrections, but I mean, in ADS, say we're doing some calculation in ADS Schwarzschild, then the geometry itself encodes the periodicity. And so if you do loops of gravitons in this background, you wouldn't expect to ever violate the periodicity. So, I mean, the expectation is that the deviations are just some exponentially small thing in the central charge. I mean, they might not actually be small everywhere kinematically, but I mean, formally there should be a non-perturbative effect. Just because you can't alter the geometry of ADS Schwarzschild by adding some loops of gravitons.
That's true for ADS Schwarzschild, but for the case with a heavy mass, a heavy operator, is it clear that the deviations have to be exponential to ideal state?
I mean, I don't know if it's clear from the sort of thermodynamic side. I mean, if you have a BTZ black hole, it also just encodes this periodicity in the same way.
I agree, but if you insert this heavy operator.
You mean if you have a heavy operator that's below the BTZ threshold? Then it doesn't look thermodynamic. It looks like, then you don't observe any periodicity at all. So, yeah, then, okay. So in a certain sense, what I'm advocating is some different perspective on thermodynamics. Instead of thinking about thermodynamics in terms of ensembles, we can think of it in terms of these microstates. But moreover, because we have, if we think about things in terms of the CFT bootstrap, then we can think about this 4-point function as coming from an exchange of states between our light probe and our heavy background. And this is exactly what it looks like we're doing when we study something like ADS Schwarzschild. We determine some gravitational field created by the heavy state, and then that gravitational field acts on the light operators and tells the light operators that we're in some thermal background. And so we can view thermodynamics as some result of interactions between the bath and the probe.
Quick, vague question.
Yeah.
Periodicity in Euclidean time, since when you analytically continue, seems to translate to either exponential growth or decay in Lorentzian time.
Yeah.
Is that a tight connection? I mean, is the
That is-
decay of quasi-normal modes a tightly connected?
I don't think it's a completely tight connection. So I mean, yeah, I don't. Yeah, I mean, for example, you can have a constant which doesn't decay, but it's periodic. So there's the,
I think the regime outside the tau from 0 to beta is somehow not relevant for analytically continuing things, because you extend it to periodic functions by definition. So the function just between 0 and beta, tau belonging to 0 and beta, determines the real-time properties.
But the fact that at 0 it's the same as beta, that is context, right?
Yeah, that you can derive from
good. So this is sort of the basic question, and you can ask whether or not you can derive black hole thermodynamics in any number of dimensions, but now we'll actually focus on ADS3 and see that this can actually be enacted using Virasoro symmetry. So as we said before, we can think of graviton states in any in ADS as being dual to the stress tensor in the conformal field theory. But something much, much simpler happens in the context of 2D conformal field theory, which is that the stress tensor decomposes into a purely holomorphic piece that depends on Z and a purely anti-holomorphic piece that depends on Z bar. And we can then expand, say, T of Z in terms of modes, where these ln's are operators. And the mode expansion of the CFT stress tensor is what gives us these operators are the generators of the Virasoro symmetry. So what that means is that all of the correlation functions of the stress tensor with any number of stress tensors are fixed by Virasoro symmetry. And in turn, that tells us, that roughly speaking says something like all quantum graviton matrix elements are fixed by symmetry. So just being very, very specific, I can imagine acting on the vacuum with the stress tensor evaluated at 0, which is L minus 2. That creates some sort of graviton state. And so I can talk about the exchange of these kinds of states in correlation functions. And just in case you find that confusing, we usually think of symmetries. One might have thought that the symmetry annihilates the vacuum. Here, L minus 2 is a symmetry generator, but it acts in the vacuum to create something non-trivial. In the context of Virasoro, it's only the global generators, L1, L0, and L minus 1, which correspond to translations, dilatations, and special conformal transformations that annihilate the vacuum. All of the other symmetry generators actually create states. So in a certain sense, if you like this language, you could say something like the Virasoro symmetry is spontaneously broken, and that's why these don't annihilate the vacuum. OK. So this is the Virasoro algebra that fixes all of these graviton correlation functions. And the central charge appears here in this form. And we're going to be interested in the large central charge limit because we're interested in the limit of small g Newton. And so we can ask, what happens to this Virasoro symmetry algebra if we imagine that C is a very, very, very large number? Well, roughly speaking, then we can just ignore this term. And if we ignore this term, then we just get a bunch of decoupled oscillators. So to some some approximation at large central charge, this is all what all the ln's do. And so what this means is that the only ln only talks to L minus n. And so when I act, otherwise all of the different ln's with different labels commute with each other. And so we can think of these as just a bunch of different harmonic oscillator creation and annihilation operators, with the L minuses being creation operators and the L pluses being annihilation operators. That's the algebra they satisfy. And this is just the statement that if you send g Newton to 0, gravitons don't talk to each other. Gravitons don't interact with each other. And so the space of graviton states is just a Fock space created by acting any number of times on the vacuum or any particular state with these L's. And furthermore, the fact that the central charge appears here just tells us what the normalizations, what the natural normalizations of these states are. If I have some number of gravitons, then the normalization of that state is just C to the power of much gravitons I have. So this means that in the limit that the central charge is extremely large, things become very, very simple. Now, what we're going to be interested in is studying an interesting large central charge limit, but where we exchange all possible graviton states. So all of the graviton states in the Hilbert space at any central charge are spanned by just acting with these L's on some definite primary state. And so we're just interested in exchanging all of them between the light operator and the heavy operator.
H can be anything.
Good. So, I mean, I made life more complicated in general than I had to. So, so I can talk about H being the vacuum. That's the simplest case. And that gives you the vacuum Virasoro block. It's the contribution of all just pure graviton states being exchanged between the heavy operator and the light operator. But I can also talk about more general Virasoro blocks, or Virasoro partial waves, which are what I get when I take a general primary state with dimension h, and I act with all these L's. And I'll have to act with L minus 1 as well in that case. But otherwise, this is the same kind of formula. And all of these objects are interesting. So the method that we're going to use to compute this in the large central charge limit will work just as well for small finite h as it does for h equals 0. So I'm going to tell you about all of them. But if you like, you can focus on h equals 0, which is the vacuum block, which is in some sense the most important one. That's pure graviton exchange.
And the periodicity you will derive will only depend on capital H.
It'll only depend on, yeah, capital H, exactly.
These gravitons all limit the boundary.
Formally, yeah. I mean, there aren't any local gravitational excitations. There are no gravity waves propagating in ADS3.
So they only interact with themselves somehow?
Well, I mean, they have non-trivial matrix elements with all of the operators that are just fixed by the word identity of the stress tensor. So I mean, they interact with everything. I mean, I mean, this idea that they live at the boundary, I think, is perhaps a little bit too strong, because these are really the states that give rise to the gravitational field of heavy particles and black holes and things like that.
An alternate way to say it might be that there's some non-locality, so if you insert some object in the bulk, sort of non-locally affects the boundary shape, so something like that, so it can affect boundary graviton.
Yeah. I mean, another way of saying it that just is sort of different is that it depends on what gauge you choose how these gravitons act. The only thing that you're guaranteed about them interpreting them in ADS is that asymptotically there's some asymptotic symmetry of ADS that turns into these graviton states. But I can fix a gauge where there's something you might call the gravitational field inside ADS, and it has a non-trivial propagator. So it's just that it's gauge dependent, sort of how that does, and you can sort of move it out towards the boundary or move it around by making different gauge choices.
Brownhill matrix. There is some kind of a Coulomb field, and there is no
Exactly, yeah.
I mean, it's useful to think of ADS free gravity as very similar to Chern-Simons theory, right?
Yeah, so one of...
So these are just vortices that sort of move around at these long range.
Yeah, so you can, I mean, you can get, in fact, these kinds of objects, this sum over all of these intermediate states, by studying Chern-Simons-Wilson lines in a particular way. So we're going to take a limit that's way, way too trivial, because that's basically all that we'll need with the methods that we're going to use in a few more.
The interaction, is it just that you've got an operator, it sort of deforms ADS a bit, and then all the boundary gravitons are these large diffeomorphisms of the operator, right?
Mm-hmm.
So that the large diffeomorphisms interact with the small deformation, the normalizable deformation. Should I think of it that way?
Yeah, I think so. I mean, here it's not like, so maybe they're irrelevant and they just live at the boundary. If you study something like you have some correlation function of some local operators, and then you just insert t, or in other words, if you just act with like L here. But here we're not just sort of acting externally on some correlator we already know, but we're exchanging all of these states between these operators. And so, I mean, there's no sense in which like it's only happening at infinity. I mean, it really affects what happens in between the light probe and the heavy operator.
Right, I'm trying to think from the point of view of the bulk. You know, these different, sorry.
Yeah.
These different boundary gravitons from the point of view of the bulk are just diffeomorphisms of the same gravitational state.
Yeah.
So it doesn't look like that much is happening there. I don't know what my question is.
So insert the heavy guy, generates a deficit angle, then you do these diffeomorphisms, and it affects the net state.
Kind of diffeomorphism.
Yeah, and it's a little quick to say it's only boundary. Now, in some gauges, it's certainly more than at the boundary.
Yeah, that's certainly true. Okay, well, I mean, in a few slides, we'll just compute what the answer is. So, okay, so if you take the infinite central charge limit and you just fix all of the other parameters that are entering into this correlation function, then you get something incredibly trivial. This normalization matrix for any non-trivial number of gravitons is just going to give us factors of c downstairs. And so if you send c to infinity while fixing all the other parameters, you just get back the exchange of only, sorry, this should have really been the vacuum here. You get only the vacuum in the vacuum case. And you just get the standard product of two different two-point functions. So that's very, very trivial.
I'm sorry, I just.
Yeah.
So suppose there are of course these special operators which are null states, where you have
Yes.
special elements that are identical.
Yeah,
So
yeah.
if I take a generic operator, there's no null states. Then the spectrum that I get starting with the primary is precisely that of non-interacting gravitons with the primary.
The spectrum is, well, I mean, the matrix elements aren't I mean, at infinite C, they're non-interacting. At finite C, you get interactions. But yeah,
at
yeah.
finite C, the spectrum is just non-interacting. Because
What do you mean by the spectrum is non-interactive? The spectrum only has integer energy levels. I mean,
suppose I compute the character
uh-huh.
of the representation, it would just be acting with harmonic oscillators for each ln treated as a harmonic oscillator.
Well, at finite C, they don't commute with each other. The ln don't commute with each other,
So it
right?
doesn't matter. Right, I mean, just
For the energy levels, I agree. I mean, the energy levels are all integer spaced. That's for sure true.
and you could just compute the whole character by treating them as
For the character, that's true.
independent of
Yeah. For the character, that's true. I mean, then you're just counting states. For the correlation functions, it's not true. Yeah. So I'm making this point that that at infinite central charge, the correlation function becomes extremely trivial because effectively we're going to find a way to make this calculation apply even in the case of a black hole, and we'll see how that works. Similarly, if you take the case where you're not studying the vacuum but you're studying some general primary, if you take the infinite central charge limit, you just get back the global conformal blocks. All of the contributions from Virasoro drop out because they have these factors of C in the denominator because of these normalizations, and so you just get a global conformal block for a 2D CFT, which is just this hypergeometric function. Exactly. So this is all very, very boring because we sent the central charge to infinity while fixing the dimensions of all of these operators. In another slide, we're going to not do that. Yeah.
Just to answer,
Sure.
means you just keep the H, the primary, in that intermediate state.
You take the primary, so L0, L1, and L-1 are still non-trivial because they're just global conformal generators. They don't know about the central charge. And so the global conformal descendants of H also contribute, and that's why you get a hypergeometric function instead of just a single monomial. But that's all that contributes.
I see. And does this correspond to the heavy field moving around in ADS being probed by the light ones, or what is it? How should we think
This
about
core, I think I would think about this as, I mean, I'm fixing the light and heavy operators in some configuration, but I'm summing over all states involving both H and different motions of H, right? Because I'm summing over all the different
functions of H, right?
of the intermediate state. Yeah, exactly.
So the heavy guy moves around, you probe it. Isn't it?
Oh, sorry. This is more like the intermediate state being
the
is.
intermediate,
Yeah.
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 I get confused,
Yeah.
different motions. Some of them are like the global guys have different motions of it.
Exactly.
Different motions and different.
Yeah. So the Virasoro ones are diffeomorphisms. The global ones are motions. Yeah. Good.
So the diffeomorphisms are dropping.
Diffeomorphism could be some though. That's the problem.
Yeah. So here we took the limit that C is extremely large, in which case all of the Virasoro modes drop out, and then we just get back the global answer. So we're going to put the Virasoro modes back in a clever way in another couple of slides.
Sorry, just a remedial.
Yeah.
The null states at large central charge, if you have a finite H,
Yeah.
are there null states?
The null states all have negative dimensions, so they're all they're all non-unitary.
So they're not important.
They're not important. They'll come back in the next talk, but they're not important here.
I think isn't it realistic to
Yeah, yeah. For c bigger than 1, it's not that they're not there. I mean, they're below the unitarity bound. They're at negative dimension. As representations, they're still there.
So in particular, this is not the thermodynamic limit at all because the answer is dependent on A in the end. Because this is the answer for this correlation function that you computed, right? Sorry, I'm a bit lost about the overall. So we were trying to compute this 4-point function and get the periodicity.
Good, good, good. So far we've only done things that are very trivial. We've basically just sent c to infinity, which means that we've just recovered global conformal answers, which don't know anything about Virasoro. So why are we doing this? The reason why we're doing this is that we're going to find a way in another slide or two to make the computation using the full Virasoro just as easy as this was. And so I'm just reviewing the fact that, that all these things drop out with that motivation in mind. So these formulas are not particularly interesting. I mean, this formula is really the only thing that you probably really want to know. This is going to turn into that formula that was periodic in Euclidean time in another couple of slides. But right now, it's just the trivial vacuum exchange. So I apologize. OK, so we already said this in a different language before. But we can ask, how do these Virasoro modes couple to other operators? And of course, they couple in a way where Lm acting on OO gives us something proportional to the dimension of the operator, or the ADS energy. That's what we said when we studied the long-range force version of this question. We said that we get something proportional to the energy of, say, the heavy guy, the energy of the light guy, divided by c. And there's some precise commutation relation that, that encodes this. So the only point that, that we're really making with this slide is that in the large central charge limit, we can compensate for c going to infinity in the denominator by some heavy operator dimension in the numerator. And that's what we're going to do and what we want to do. What'd you say?
Of the external operators.
Of the external operators, exactly. So I mean, for example, there's a Newtonian limit where we fix this product over c. That's a thing that we could do. But we're going to study the more interesting limit where we actually have something like a black hole. And so we want to study this real heavy light semi-classical limit where you have a black hole and then some probe friend who's interacting with the black hole. And so what we'd like to do in order to get some non-trivial answer is to study this heavy light semi-classical limit where h heavy is proportional to c as c goes to infinity and h light is some finite number. In that way, we can get factors of h heavy in the numerator for every Virasoro mode we couple to. We also get factors of c in the denominator for every Virasoro mode we couple to. And so we'll get some interesting non-trivial finite limit. And so now the question is, how do we compute the Virasoro blocks in this limit?
But is there a sense in which the thermodynamical limit means that C and H came in the same way?
So I think in ADS 3 CFT2, this is the way that you want it to scale. I think that's also true in higher dimension, but I mean, for sure in this case. So here, I mean, notice that we're working on a finite spatial circle. So, so we're not getting thermodynamic limit by taking, say, infinite volume, which is what one might normally do. Instead, we're getting it by taking infinite central charge, and this is this will turn out to be the right limit to take.
This is the limit in which back reaction is order 1.
Back reaction, from the heavy state is order 1. Yeah.
So just to understand, you'll scale h heavy with c,
Yes.
but not scale h light.
Exactly. So, great. So the question is, how can we actually compute this sum over all possible Virasoro states in this limit? And it turns out that at this point, there are a lot of different ways that you can do this. So I listed some of them here. There's an old, clever technical trick that I'm not going to use, though we originally used it. There's a way of doing this by brute force. So you can actually brute force sum over all of these multi-Virasoro exchanges. It turns out that there's a bunch of nice mathematical simplifications that happen that maybe didn't have to happen, but do, and so you can actually just do this all directly if you want. But then there's a much more physical way of getting the answer, which I'll refer to as the background field method, and that's what we're going to use in the rest of this talk. You can also compute these exchanges using Chern-Simons-Wilson lines in various ways. And you might ask, why do all these methods exist? I mean, at least for the ones that I was involved with, really these all exist because I was looking for some way of generalizing these ideas to higher dimensions, and I failed, but I found a lot of different ways of deriving the same thing in 2D. Good. So the idea of the method is to find some sort of background that trivializes the exchange of the Virasoro modes. So you can say it like this. If one way of computing the full nonlinear gravitational field in gravity is to sum all of the Feynman diagrams that contribute in the semi-classical limit. You can try to do that brute force sum, but a much better way of figuring out what the gravitational field is to solve for a classical configuration of the gravitational field, and then once you're working in that background, there aren't any small fluctuations around it that continue to dominate. Basically, you found the right background for the calculation. I mean, that's all completely trivial. We all learned that in kindergarten for gravity. But the question is, can we find equivalently a background in the CFT and expand around it so that we sort of trivialize the calculation? We absorb all of these apparently non-trivial gravitational effects into some new metric. So that's the idea. And in ADS3, CFT2, you can do this. So everything I'm going to say for the next few slides is really just CFT calculations. You don't need to know anything about gravity to do this. And one way of motivating it is to ask why the stress tensor isn't a primary operator. So primary operators are things that under a conformal transformation, which in 2D conformal field theory can be some general holomorphic transformation from the z coordinate to some new metric parameterized by w of z. Primary operators are supposed to transform in this very, very simple way. So for example, you see that if you have some primary operator that has no vacuum expectation value, and you transform to you put the CFT in some new metric via a conformal transformation, then it still will continue to not have a vacuum expectation value. The stress energy tensor doesn't transform in this way when we transform the background metric in which the CFT lives. So here we are transforming the background metric from a flat metric to some metric parameterized by some, it's conformally flat, but it's not exactly flat because it depends on this w prime of z function. Now, if we transform to live in this new space, generically you might expect that the stress tensor is going to get a vacuum expectation value. I mean, we've sort of, basically there should be some Casimir energy associated with the fact that we've bent our metric. And so in a certain sense, this is why the stress tensor can't be a primary operator, because we expect that when we transform to a new background, it has to get a VEV. And formally, what this, the correct transformation property for the stress tensor is that it has this piece that looks like the transformation law of a primary, but it has this extra Schwarzian derivative piece, S. And so the Schwarzian derivative piece is basically, you can think of physically as capturing the fact that the stress tensor got a VEV in a new coordinate system. So the question is, can we use this to somehow trivialize our calculation? So we're trying to sum over the exchange of all of these Virasoro modes between our heavy operator and our light operator in a limit where back reaction from the heavy operator is very, very, very important. But doing the sum directly is kind of like summing all of the Feynman diagrams. If we can instead just find the right background, then maybe we can trivialize things. So all of the complications of doing this calculation come from the fact that the correlator of the heavy operator with the stress tensor and anything else, but for example, some specific primary state, has this term which is proportional to h heavy. And remember, we're taking h heavy to infinity along with c. So this is some sort of big effect, and this is why this is why there's non-trivial back reaction. So the question is, can we transform to a new coordinate system where this term doesn't appear and there's nothing of order h heavy coupling the stress tensor to the heavy operator? So it turns out that, of course, the answer is yes. If we transform to a new coordinate system, a new background metric, w, defined in this way, where the parameter alpha takes this particular value in terms of H heavy in the central charge, then if we just use this transformation rule for all of the operators in this correlation function, specifically the stress tensor, then the Schwarzian derivative term for the stress tensor balances and cancels out against the term that was circled on the last slide, this effect. And we get something that doesn't have any H heavy dependence at all. So all of the H heavy dependence in this correlator was absorbed into by this new choice of background. So this is supposed to be the right background. So what is the physical interpretation of this background? Well, it actually does have a very nice interpretation in ADS. So we saw that this parameter alpha appeared in our relation between the z and w coordinates. If we sort of naively map the z and w coordinates into the bulk, then they have this kind of relation. And what this parameter alpha turns into is it's either a measure of the deficit angle, if it's real, or it turns out to be a measure of the Hawking temperature if it's imaginary. So you see that in this alpha, this is the absolute value of alpha for this being large, but there's this square root. And so for a certain range where this parameter is less than 1, alpha was real, and when this parameter becomes bigger than 1, alpha becomes imaginary. That's the transition between a deficit angle in the bulk and a BTC black hole.
So can you,
Yeah, yeah.
explain for this? So how did you deduce that this should be the transformation to motivate? In the sense that was it the finite coordinate transformation that would allow you to?
Good. So you can solve a differential equation. Say if you didn't know that this was going to be the answer, you know that this is the transformation rule, and this Schwarzian is just involves some derivatives of z with respect to w. So you could just work it out. So you can write down a differential equation for this transformation, demanding that this H heavy term cancels, and you can solve that differential equation. Now, you might have known ahead of time that this is the right thing to do physically, because as of course it's going to turn out to be the case that this tells us about the black hole temperature and deficit angles, et cetera. And so you could have guessed that this is the right thing to do. In effect, this is basically transforming the CFT to a thermal cylinder with the right temperature. Basically, if you do that transformation, then you get rid of this H heavy dependence.
Before you,
yeah.
as you said, the BTZ sort of undoes or puts in the deficit angle, right? The 1 minus z to the alpha.
Exactly. So here, yeah, this is exactly like something like a deficit in the metric. Exactly. Yeah.
And could you go back to the previous slide?
Sure.
See, you had this, I think so one of the OHs is at infinity, that's why you have only one.
Exactly. So we chose OH is at infinity and 1, and O light is at 0 and z, I think, and this, though possibly change.
So basically, we just put the heavy operator in at 1.
Yeah. Exactly. Yeah, so if the heavy operators were generic locations, this would be some ratio of, yeah. Good. Okay. So now, I mean, to actually finish the calculation, so we found this new metric, but we have to formally set up the correct exchange of Virasoro modes. So now we have the stress tensor not in the original coordinate system. We have a new stress tensor in this new W coordinate system. And it has some expansion in terms of new Virasoro generators. So this is very much like the fact that you can talk about gravitons in, say, flat space, or you can talk about gravitons as excitations around, say, a black hole solution, and those are two different sets of modes. I mean, one of them is the set of modes of the vacuum, the other one around the new background. So these are sort of like Virasoro fluctuations around this new background. Now, a fact that is very important here is that although we have new Virasoro generators, they actually obey the exact same algebra. They still obey the Virasoro algebra. And this is due to the fact that the Virasoro algebra is a consequence of the OPE of the stress tensor with itself. And the stress tensor in different coordinate systems has the same OPE. So these new L primes, these new kinds of gravitons obey the same Virasoro algebra. But now, instead of computing the exchange of all of the gravitons in our original background with the original Virasoro generators, we could compute the exchange of these new L prime Virasoro generators in our new background. And now, of course, this is where the payoff comes. All of these L primes that are not global generators act trivially at large central charge because they still have a normalization, which is large when C is large, but we neutralized the H heavy part that was going to compensate in the numerator. So in other words, we accounted for all of the back reaction. And so this correlates. So this sum over states now truncates to the global conformal generators, but the global conformal L primes, not the original L's.
In the new coordinates, where are your 4 insertions, please?
The 4 insertions are formally in the same place. So, sorry. 1 maps to 1, and infinity maps to infinity. 0 also maps to 0. But we had one operator that was at Z, and now it's at W, where W is 1 minus e to the alpha.
So suppose I was just directly doing the calculation in the new coordinates. Why would I then conclude, that's a stupid question, but why would I then conclude that if I took the operator near the stress tensor, I would get this root? The stress tensor near the heavy operator, I get the root.
You mean like why would you see that this cancels, or? I mean, I think if you just do the naive calculation, well, you would have to include the fact that the stress tensor has a VEV, which is given by the Schwartzian. And I mean, if you didn't know why you were using this coordinate system, you would think that there was some miracle that was happening such that the stress tensor VEV was always canceling the contribution. Yeah, I mean, that's.
In those coordinates, you also see a conical angle response, right?
Yeah, so that's true. So it's unclear. You can ask, what does this mean, sort of in some global sense? And I don't know. In this, like, we're now putting the CFT in some weird new coordinate systems. You might worry that there's some sort of global issues. As a matter of fact, I mean, for computing the sum over the exchange of states, this gives us exactly the right answer. But I mean, you can worry about there being some problem if you come close to these conical deficits, etc.
And in particular, the conical deficit is at the location of the heavy operator.
It's at the location of the operator. So I mean, there was something non-trivially happening there anyway. But yeah.
No, but it's the place where the cancellation happens.
Yeah.
It's the place where you've brought it.
Exactly. Yeah. Yeah. Good. So now, I mean, now you see why we did the completely trivial calculation 10 slides ago.
Just
Yeah.
a sec.
Yeah.
So this the Schwartzian derivative is a delta function localized at that location?
No, the Schwartzian derivative is, it's not delta function. I mean, the Schwartzian derivative has to cancel this functional dependence. So it depends on where you are. Okay. Good. So to roughly speaking, now we just get the computation of the global conformal blocks in this new coordinate system. And so in fact, in the limit where we just have heavy light operators, we actually get exactly the same function that we had before for a global conformal block, but evaluated as a function of this new variable W. Because we already absorbed all of the gravitons into the background. And so this is some computation entirely in the CFT. The important point with respect to black hole thermodynamics is that this change in coordinates already exhibits the Euclidean time periodicity. So if H heavy is bigger than C over 24, so that alpha is imaginary, then alpha is just 2 pi times the Hawking temperature associated with the BTZ black hole of bulk mass given by H heavy. And we see this Euclidean time periodicity. If we rewrite this in terms of the Euclidean time coordinate, this W coordinate is just explicitly periodic with period 1 over T Hawking. So basically, once we found this new coordinate system, we were sort of guaranteed to learn about black hole thermodynamics. And so the simplest example here is the vacuum conformal block, which is the exchange of just pure graviton states without any other primary coming along for the ride. And so the Virasoro vacuum block in this heavy-light limit, where the central charge went to infinity proportional to h heavy, is just given by this simple formula. If we rewrite it, instead of z, we use cylindrical to coordinate t. It just takes this very nice form. It's just explicitly periodic in Euclidean time. And this looks exactly like a thermal correlator at temperature T. But although, I mean, this is the vacuum block. It's very nice. I mean, all of the other Virasoro blocks for intermediate primaries H, small compared to C, also exhibit the same kind of dependence on this W coordinate, the same periodicity. So sure. Yeah, so I can finish in 5 minutes. So I mean, this is the basic punchline. I was just going to say a couple of other things.
But you know, can I make a suggestion? It's a
Yeah.
beautiful presentation,
Oh, sure.
if I may say, which is, without you are rushing through,
Yeah.
can we continue it tomorrow?
But he has 2 more lectures.
So I'm just saying,
Sure. Yeah, I can.
rush through it too fast.
Yeah, sure. Yeah. I mean, yeah.
I mean, just because this is some formally colloquial or whatever it is.
Sure. Yeah. So I was just going to make a few other speculative comments about how you might try to about either how you might try to drive this in higher dimensions, or conversely, what the same kind of considerations tell you about the data of the theory. In other words, what's the relationship between OPE data and thermodynamics in holographic theories? So if you just sort of rephrase everything that we did in more general terms, then what I'm essentially telling you is that if you talk about the exchange of stress tensors and all of the states built from multi-stress tensors, the things that in a large N theory you'd call multi-trace operators built from the stress tensor, if you talk about the exchange of all of these things between light and heavy operators, then you get a thermal correlator. This is just restating in terms of the OPE the familiar fact that you solve Einstein's equations in ADS with some heavy source, you get a black hole, and that automatically, just by virtue of the black hole geometry, gives you black hole thermodynamics. So in other words, I guess it's interesting to ask, what do we know about these kinds of the OPE coefficients or the correlation functions of these kinds of operators? And of course, for the single stress tensor, we know a lot. It's just forced to take a certain form by Word identities. But for all of these other operators, I think we know very little that we can say precisely. Now, in order to say something sharper, it's useful to take a further limit, which is to take the high temperature limit, or in other words, the limit that we decompactify the spatial circle that we're living on. So everything that I've done so far has been living on this compact space. Yeah.
Unlike in 2+1 dimensions, in higher dimensions, these stress tensors will not in general close among themselves.
Absolutely. So in higher dimensions, they will not close among themselves. There's some set of theories that we think of as some set of holographic theories where they don't necessarily close among, I mean, they certainly interact with everything else, but somehow these dominate the thermodynamics. Even if we have some other light fields in the bulk, like say we have some black hole with some small charge, there's some mixing of the stress tensor and the current and multi-trace states made from those that somehow gives rise to the temperature of, say, a charged black hole. So there's some nice thing that's happening where when you sum over all of these things, you get something thermodynamic. Yeah.
If you take the large central charge limit, if I go back.
Yeah.
I mean, the LNs basically became free oscillators.
Yes.
And you'd expect something similar here, right?
Absolutely. So at infinite n, I mean, the normalization of the stress tensor is proportional to n. So I mean, at infinite n, you would expect that you just get mean field theory or a generalized free theory built from the stress tensor. But I mean, in order to actually get the correct answer that we obtained, it was necessary to go way beyond the approximation where we just treated the LNs as independent oscillators. So somehow you have to do that here as well. Yeah, this is all very speculative. I'm not proving any theorems right now.
The answer is universal in 2 dimensions. N equals for animals, the answer will depend on lambda.
Absolutely. So the question, exactly. So but the question is, what does it depend? I mean, it's phrased in terms of CFT data. What does it depend on? So yeah, let me just say, you can take a further limit that simplifies things more, which is to take the high temperature limit. The high temperature limit on a compact space is the same as decompactifying the space. So in other words, what you're doing is you're sort of measuring the CFT correlator in units rescaled by the Hawking temperature. And so this is sort of a picture that the black hole's growing out, and basically you're just now living on a plane rescaled by its temperature. This is equivalent to just working at infinite volume and finite energy density. So you could try to study heavy states that are so heavy asymptotically that they just look like some finite energy density background. In other words, they would be black brains in ADS. And you can ask, what contributes if you take this limit? And it's actually very simple. Only the exchange of stress tensors without derivatives contribute. So on an earlier slide, we had not just T mu squared, et cetera, but things with all sorts of derivatives. Here, in this extreme high temperature limit, it seems like the only things that contribute are just these operators. So
The derivatives are so small.
because the derivatives are so small, because they've been rescaled by space being big. Yeah, exactly. So
Sorry, but just it sounds plausible, but those derivatives are hitting these are appearing in intermediate states, right?
So what happened was we were. So if I look at the exchange of some operator, and I mean probably we're going to run out of time now.
Yeah,
And,
you
and
can tell me. You can
okay,
tell me.
okay. Well, no, but I mean we can just run out of time, and then we can finish next time. So.
Speaking of which, I think we should finish it.
Okay, well, why don't we just conclude there? I can tell you about this, and then I'll finish this next time, and then we'll move on. So.
Really sorry.
Oh yeah, no problem.
Then a quick question.
Yeah.
Everything will go through with a minimum momentum?
Yeah. So in fact, I sort of brushed a lot under the rug because I only talked about the holomorphic sector. Really, so if you have a scalar heavy operator, then H heavy and H heavy bar are the same, and you just get a temperature. But in general, if you have a spinning operator, H heavy and H heavy bar are not the same, then you get a sort of left moving and a right moving temperature, and that just corresponds to the fact that the black hole is